this video, we'll discuss the proper grounding procedure for 75 kVA transformer system, specifically addressing a situation where an existing installation has an incorrect grounding configuration. We'll examine why a ground rod connected only to a panel board is insufficient and how to establish a code-compliant grounding system by connecting the grounding electrode conductor, or GEC, directly to the service electrodes. In the scenario described, there's an 800 amp main panel board feeding a 480 to 208Y/120 volt 75 kVA transformer. The primary side wiring consists of 3 number 1 wires and 1 number 6 ground wire. The secondary side has 4 250 kcmil wires and 1 number 2 ground wire. The transformer feeds a 225 amp main breaker panel board. A contractor installed a ground rod and connected it to the panel board using a number 2 grounding electrode conductor. However, this ground rod is not connected to any other part of the building's electrical system. The first issue to address is the legality of this installation. No, the described setup is not legal according to standard electrical codes such as the National Electrical Code, or NEC. The primary reason is that a ground rod, by itself, connected only to a subpanel, does not provide an adequate low impedance path to ground for electrical faults. A properly grounded electrical system is designed to quickly trip a circuit breaker or fuse in the event of a ground fault, preventing electrical shock hazards and minimizing damage to equipment. To achieve this, the grounding electrode system must be interconnected and bonded to other grounding electrodes, such as building steel, metallic water pipes, and other available electrodes to create a comprehensive grounding network. The purpose of this network is to provide multiple paths for fault current to return to the source, thereby lowering the overall impedance of the ground path. A single ground rod offers a high impedance path, which can hinder the rapid clearing of ground faults. Secondly, let's consider whether the contractor can wire a grounding electrode conductor from the panel board straight to the 800 amp service electrodes, given that building steel is not available as a grounding electrode. Yes, if building steel is not available as a grounding electrode, the contractor can and should run a grounding electrode conductor, or GEC, from the panel board directly to the 800 amp service electrodes. This provides a proper and code-compliant ground path for the installation. The National Electrical Code, or NEC, outlines acceptable grounding electrodes and methods for establishing a grounding electrode system. When building steel is unavailable, other approved electrodes must be used and interconnected. Connecting the GEC to the service electrodes is a common and effective method for ensuring a low impedance ground path. Now, let's outline the recommended procedure for correcting the grounding issue. Firstly, disconnect the existing number 2 grounding electrode conductor, or GEC, from the panel board and remove the ground rod. This is necessary because the existing installation is not code compliant and needs to be replaced with a proper grounding connection. Secondly, run a new number 2 grounding electrode conductor, or GEC, from the panel board to the 800 amp service electrodes. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Ensure that the grounding electrode conductor is long enough to reach the service electrodes without any splices. Thirdly, connect the grounding electrode conductor to the service electrodes using appropriate connectors. Use listed and labeled connectors suitable for grounding purposes. These connectors should be designed to provide a secure and low resistance connection between the grounding electrode conductor and the service electrodes. Common types of connectors include compression connectors, set screw connectors, and exothermic welds. The choice of connector will depend on the specific application and the materials being joined. Fourthly, ensure all connections are tight and secure. This is crucial for maintaining a low impedance ground path. Loose connections can introduce resistance, which can impede the flow of fault current and compromise the effectiveness of the grounding system. Use appropriate tools, such as torque wrenches, to tighten connectors to the manufacturer's specified torque values. Fifthly, test the grounding system to verify proper operation. After completing the grounding installation, it is essential to test the system to ensure that it is functioning correctly and that a low impedance ground path has been established. Several tests can be performed, including a ground impedance test and a ground continuity test. A ground impedance test measures the impedance of the ground path from the panel board to the service electrodes. The impedance should be as low as possible, ideally less than 1 ohm. A ground continuity test verifies that there is a continuous and uninterrupted path between all grounding points in the system. This test can be performed using a multimeter or a continuity tester. In addition to these steps, it is important to consider the following factors when grounding a 75 kVA transformer system. Firstly, bonding. Bonding refers to the practice of connecting all metallic parts of the electrical system together to create the common ground potential. This includes metal conduits, equipment enclosures, and other non-current carrying metal parts. Bonding helps to minimize voltage differences between these parts, reducing the risk of electrical shock. Secondly, the neutral to ground bond. The neutral to ground bond is typically established at the service entrance. This bond connects the neutral conductor to the grounding electrode system, providing a path for neutral current to return to the source. It is important to ensure that the neutral to ground bond is properly sized and installed according to code requirements. Thirdly, grounding electrode system. The grounding electrode system should consist of multiple grounding electrodes such as ground rods, ground plates, or metallic water pipes, interconnected to form a comprehensive grounding network. The NEC specifies the minimum requirements for grounding electrode systems, including the number and type of electrodes required, as well as the methods for interconnecting them. Fourthly, documentation. Maintain accurate records of the grounding system installation, including the size and type of grounding electrode conductor, the location of grounding electrodes, and the results of any tests performed. This documentation will be helpful for future maintenance and troubleshooting. Now, let's address the specific code references that apply to grounding requirements. NEC Section 250.24 covers the grounding of service-supplied alternating current system. This section outlines the requirements for establishing a grounding electrode system and connecting it to the service neutral. NEC Section 250.50 covers the grounding electrode system installation. This section specifies the types of grounding electrodes that are permitted, as well as the methods for installing and interconnecting them. NEC Section 250.66 covers the size of the grounding electrode conductor. This section provides a table for determining the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. NEC Section 250.166 covers the grounding electrode conductor connection to electrodes. It provides the requirements for the connection hardware of the grounding electrode conductor to the ground rod itself. In summary, correcting the grounding issue in the 75 kVA transformer system requires disconnecting the existing ground rod, running a new grounding electrode conductor from the panel board to the 800 amp service electrodes, ensuring all connections are tight and secure, and testing the grounding system to verify proper operation. By following these steps and adhering to the National Electrical Code, or NEC, you can establish a safe and effective grounding system that protects against electrical shock hazards and minimizes damage to equipment. Also, when referring to equipment grounding, the equipment grounding conductor ensures that all metallic enclosures of electrical equipment are properly grounded and bonded together. This conductor provides a low impedance path for fault current to return to the source, tripping the overcurrent protective device, such as the circuit breaker or fuse, quickly in the event of a ground fault. The equipment grounding conductor is typically run with the circuit conductors and connected to the equipment grounding terminal in the panel board and to the metallic enclosure of the equipment. Its size is determined by the size of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. The purpose of equipment grounding is to limit the voltage on metallic enclosures to safe levels during a ground fault, reducing the risk of electrical shock to personnel. Proper equipment grounding also helps to minimize electromagnetic interference, or EMI, and improve the performance of sensitive electronic equipment. The equipment grounding conductor should be installed in accordance with NEC Article 250, which provides detailed requirements for equipment grounding and bonding. The importance of proper grounding cannot be overstated. A properly grounded electrical system is essential for the safety of personnel and the protection of equipment. Grounding provides a low-impedance path for fault current to return to the source, tripping the overcurrent protected device quickly and preventing electrical shock hazards and minimizing damage to equipment. Grounding also helps to stabilize voltage levels and reduce electrical noise, improving the performance of electrical equipment. The NEC provides detailed requirements for grounding and bonding, and it is important to follow these requirements carefully to ensure a safe and effective electrical system. If you are not familiar with electrical codes and practices, it is best to consult with a qualified electrician to ensure that your electrical system is properly grounded. Improper grounding can be dangerous and can lead to serious consequences. By understanding the principles of grounding and following the code requirements, you can help to ensure a safe and reliable electrical system. Also, always remember to de-energize electrical circuits before working on them and to use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself from electrical shock and other hazards.